Welcome to the debate.
Today, our focus is on a phenomenon many of us working with large language models are, well, all too familiar with: slop.
Right. And we're not just talking about awkward phrasing. This is about the severe, almost mathematically obvious overrepresentation of certain words, certain patterns that make AI output feel repetitive, stale, sometimes instantly recognizable as machine generated.
Exactly. Our own forensic analysis, the one grounding this discussion, turned up some frankly shocking examples. Things like a specific character name, Ilara, showing up over 85,000 times more often than in human writing samples.
85,000, yeah. Or those sensory cliches, like heart-hammered ribs appearing almost 1,200 times more frequently. It's not just an aesthetic issue. This slop degrades quality and becomes a real headache for actual deployment.
So the material we're digging into today introduces something called the Antislop framework, and it proposes two pretty distinct technical approaches to tackle this.
That's right. First, there's the anti-slop sampler, which operates at inference time when the model's actually generating text. And second, there's final token preference optimization, or FTPO, which is a training time solution, essentially fine-tuning the model itself.
Which brings us to our central debate question for today. It's really a strategic one. Which of these two core mechanisms, the inference time control offered by the sampler or the training time optimization of FTPO, offers the more, let's say, viable, scalable, and maybe architecturally sound long-term solution for deploying high-quality LLMs?
And our positions are fairly clear. I'll be arguing that FTPL, because it embeds this slop suppression permanently into the model weights, is the strategically superior path forward, especially for deployment at scale.
And I'll be championing the anti-slop sampler. I believe its precision, the demonstrable qualitative benefits, and the level of absolute control it offers make it the better choice, even when you factor in its significant performance cost.
Okay, I understand the appeal of the sampler, especially its, immediate and precise results. But let me start by framing this from the perspective of actually getting these models out there, working in production. I believe FTPO is the superior strategy mainly because it preserves inference speed, high throughput. And frankly, that's often non-negotiable for any large-scale LLM application. The whole idea with FTPO is about making a surgical correction, baking that slop suppression right into the model's parameters permanently. And the data we have really backs this up. You look at the sampler, depending on how many patterns you're trying to ban, maybe up to 8,000 patterns, it can absolutely tank your throughput. We're talking reductions of up to 96%.
It's a heavy cost, yes.
It is. Whereas FTPO, even when fine-tuned against that same large 8,000 pattern ban list, manages to maintain the model's baseline token generation rate. That's huge. And crucially, FTPO still gets you very strong suppression, typically around 90% with really minimal collateral damage. We're seeing less than a 1% hit to overall writing quality metrics. And interestingly, it maintains or even slightly improves lexical diversity, keeping it between, say, 95% and 102% of the baseline model's scores. This stability, compared to previous fine-tuning attempts like DPO, is absolutely key.
Okay, I approach this somewhat differently. Raw inference speed is, of course, a critical factor in enterprise architecture. I don't deny that. But we have to ask, what's the real cost of that final 10% or so of slop that FTPO, by your own numbers, leaves on the table? For me, the sampler's true value isn't just its direct control. It's the ability to deliver superior qualitative outcomes precisely because it hits 100% suppression.
Superior quality is the claim.
Well, the data shows it. The sampler is the only method discussed in the material that achieves that perfect suppression while also, and this is important, improving the overall writing quality above the original baseline model scores. That's not a trivial achievement.
How does it manage that?
It's down to the mechanism, which is quite elegant, really. It's not just crude token banning. When the sampler anticipates the model's about to generate the first token of a pattern we flagged as unwanted, could be a short cliché, could be a longer sentence structure, it essentially hits rewind. It backtracks to that decision point, dials down the probability of that specific offending token, and makes the model resample, forces it to choose a different path, a non-slop sequence. This kind of recursive checking preserves the flow, the coherence, without just wrecking the model's vocabulary or making it incoherent, which is what you see with simpler token banning, especially when you try to scale that up to large band lists. So for applications where absolute editorial quality or maybe compliance is the top priority, I argue the sampler's perfect suppression justifies that computational overhead.
I do see the argument for that guaranteed 100% compliance. It's compelling for certain use cases. But let's really stare at this trade-off, throughput versus suppression efficacy.
Okay.
You acknowledge FTPO gets somewhere between 83% and 92% suppression on these large band lists. Achieving that last, say, 8% to 17% with the sampler comes at what I'd call an astronomical cost. Using the sampler with that 8,000 pattern band list, the numbers show the token rate dropping from nearly 4,900 tokens per second down to just over 310. That's sacrificing about 94% of your processing speed.
It's significant, yes.
I'm just not convinced many enterprise clients, or really any large-scale deployment, can realistically absorb that kind of performance hit simply to chase down that last fraction of slop. FTPO tackles the bulk of the problem efficiently. It addresses the deep-seated repetition globally, permanently within the model structure, and crucially lets us maintain maximum inference speed. FTPO feels designed for the 99% of deployments where efficiency and cost effectiveness are really the primary drivers. Accepting 93-92% suppression seems like a very scalable and pragmatic solution in that context.
That drop from, 4,900 down to 3,100 tokens per second, it is a staggering number. I won't dispute the math. But I might frame that reduction differently. Maybe not as a strategic failure of the sampler, but perhaps as an indicator of just how difficult and maybe how necessary it is to truly root out these deeply ingrained, high-probability slop patterns.
Necessary, you say?
Well, consider this. That final 8% to 17% of slop that FTPO misses could very well contain the most egregious stuff, the most brand-damaging or editorially unacceptable material, maybe. Those specific character names that just shouldn't be there, the absolute worst cliches or direct violations of a mandated style guide. If a publisher, for example, guarantees a client that a specific phrase or style element will never appear, then 90% suppression is functionally the same as zero suppression. The forbidden pattern will still slip through, probably too often for comfort.
Okay, the guarantee matters in those cases.
Exactly. The sampler provides that guarantee, and furthermore, the sampler offers a kind of dynamic capability that FTPO just structurally cannot. You can turn the sampler off or adjust its strength based on the specific user request at that moment. Once FTPO is trained, that suppression is baked in. It's permanent, it's global, regardless of the context. The sampler offers runtime flexibility.
That's a fair point about dynamic control, but let's maybe dig a bit deeper into why FTPO seems to be a more robust and stable architectural choice overall, moving beyond just the raw speed versus suppression numbers. We need to understand why FTPO appears to succeed where previous fine-tuning methods aimed at similar goals have often, failed quite spectacularly.
Okay, let's look at the technicals.
Right. If you look back at models fine-tuned with methods like, say, direct preference optimization, DPO, trying to impose these kinds of stylistic controls often led to, frankly, catastrophic performance collapse. DPO-tuned models frequently showed significant degradation on core reasoning benchmarks, things like MMLU, GSM-8K, sometimes dropping 2, 3, even 5 percentage points. They also often suffered a dramatic drop in overall writing quality, losing maybe 6 to 15 points on the evaluation rubric, and their lexical diversity just plummeted.
DPO definitely had its issues with stability when pushed hard on preference tasks.
Precisely. FTPO seems to avoid this kind of structural damage because of its more precise, almost surgical design. And this is where the academic details become really important. FTPO operates in logit space, which is key. And critically, it uses a mean squared error MSE loss that explicitly tethers the adjustments back to the original reference model's logits. This seems to be a crucial innovation.
Mm-hmm. The tethering mechanism.
Exactly. By using MSE loss for this tethering, you're essentially just nudging the probabilities related to the specific slop vocabulary you want to suppress. You avoid putting that sort of excessive collateral pressure on the model's entire vocabulary distribution, which is often what happens with methods using standard divergence measures like KL loss. FTPO basically keeps its hands off the vast majority of the model's linguistic knowledge, which helps preserve those core capabilities like reasoning and, basic factual recall.
I appreciate that breakdown of FTPOs. Let's call it technical resilience. DPO's known failure mode, that sharp collapse in performance after hitting maybe just 40% preference accuracy. FTPO does seem to mitigate that quite well with its gentler, tethered approach. It allows training to much higher preference accuracy without causing that kind of degradation. So, yes, I'd agree, FTPO represents a significant step forward compared to DPO for this specific task. Non-destructive preference optimization.
Right.
However, even the most sophisticated preference optimization, like FTPO, still primarily works by adjusting localized token probabilities. It changes the model weights to make it less likely to generate certain patterns. And this brings us back to the sampler's unique advantage, its functional flexibility, especially when dealing with more complex, structural slop, the kind of stuff that fine-tuning inherently struggles with.
What kind of structural slop are you thinking of?
Well, FTPO fine-tunes the model to dislike common sequences, but the sampler can enforce constraints on much longer-range structures using things like regular expression bands. That's a level of control FTPO just isn't designed for. We saw this in the material when targeting that verbose repetitive sentence structure. It's not X, it's Y. Using a regex band in the sampler completely eliminated it. 0.00 hits per 1,000 characters. The baseline models, meanwhile, were churning it out maybe 0.5 to 1.1 times per 1,000 characters. Achieving that kind of structural enforcement purely through token-level fine-tuning is, well, it's incredibly difficult, maybe impossible without side effects.
Regex bands are powerful.
They are. And moreover, the sampler provides that vital capability of soft banning. This is a really nuanced feature that FTPO's permanent suppression just doesn't have. FTPO essentially says, this pattern is bad, suppress it always. But the sampler allows for context. It has that configurable band strength parameter, denoted as S. This lets a generally banned word, maybe tapestry, if it's statistically overused in fiction outputs, still be used if the context strongly demands it. Like, if a user explicitly asks for an essay about tapestries, the sampler's soft banning can allow the word tapestry if its probability gets high enough, which avoids the model getting stuck or producing incoherent output because it has no viable alternative words.
Okay, that's a very strong point about the sampler's architectural flexibility. The regex bands for complex structures, the necessity of soft banning for context, that level of immediate dynamic control is certainly powerful, I grant you that.
Right.
But we have to come back to the initial strategic question. While the sampler clearly excels at that kind of micromanagement, those high compliance tasks, FTPO addresses the core widespread issue that really affects all deployments, the automatic, almost reflexive generation of statistically common, often low-effort language.
The bulk of the slop.
Exactly. The vast majority of slop, whether it's Ilera popping up everywhere or the constant part-hammered ribs, it's fundamentally statistical in nature. It comes from biases in the training data that inflate the probabilities of these patterns. And the automated pipeline described, using the sampler's own inference traces to generate the training data for FTPO, ensures that the most frequent and arguably most problematic patterns get addressed globally, permanently, right there in the model weights. By implementing FTPO, we ensure the suppression is, well, always on, universally applied, and crucially, it incurs zero recurring runtime cost. So for the broad, efficient elimination of these overused stylistic habits, which I'd argue is the primary goal for most large-scale, cost-sensitive deployments, whether creative or functional, FTPO seems to provide the superior strategic approach. It corrects the model's fundamental biases without imposing that crippling operational overhead day after day. So, to wrap up my position, FTPO really demonstrates that high-performance, permanent slop suppression is achievable without forcing developers into that difficult choice of sacrificing core operational needs like inference speed and benchmark performance, which are essential for production LLM serving. The technical innovations discussed, like the logit space operation and the careful regularization that avoids the failures we saw with earlier methods, offer what I see as the most robust and strategically sound long-term path for mitigating these widespread quality degradation issues. FTPO optimizes for scale and efficiency.
And I would frame the final comparison a bit differently. I think the choice really boils down to the specific application's top priority. The Antislop sampler, in my view, provides the ultimate guarantee of quality and compliance. Achieving that perfect 100% suppression, combined with its much more flexible control mechanisms, like enforcing complex structural rules with regex, and the essential nuance that soft banding provides, offers a qualitative and functional edge that fine-tuning, just by its nature, struggles to fully replicate. So the decision facing developers seems clear. Do you prioritize raw computational speed and scalability, leaning towards FTPO, or do you prioritize absolute output quality, fine-grained control, and dynamic adaptability, which points towards the Antislop sampler? Both strategies, however, and I think we agree on this, mark a really profound and necessary step forward in tackling LLM degradation. We're moving well beyond simplistic, often destructive token banning. The material gives developers clear, evidence-based pathways to actually tailor their slop reduction strategy to whatever their specific needs might be.
All right, so let's dive into some new research that tackles one of the most, well, annoying problems with AI writing today. I'm talking about its tendency to fall back on the same tired, repetitive phrases. A new paper presents a framework called Antislop, and it might just be the cure for AI's bad writing habits. If you've ever used an AI for creative writing, you've seen this. I guaranteed it. Or at least phrases just like it. It is a dead giveaway that you're reading text generated by a machine. This kind of repetition, this is exactly what the researchers are targeting. It just feels lazy, uninspired, and frankly, it's everywhere. So here's our game plan for this explainer. First, we're going to define what AI slop even is. Then we'll look at how the researchers basically put it under a microscope. We'll check out their first attempt at a fix and its major drawback before we get to the real breakthrough. And finally, we'll see the results and talk about what this all means for the future. Okay, Section 1. Let's get right into it and formally introduce this concept of slop. It's a term that just perfectly captures that feeling of wading through, low-quality, repetitive AI text. This is really the question at the heart of the whole paper. I mean, whether it's for work or just for fun. If you're a heavy user of large language models, you've felt this. There's this undeniable sameness, right? A lack of diversity that makes the text feel super stale and predictable. The researchers wanted to figure out exactly why that is. And here we have their form. All right, there's this undeniable. All right, so first original word to continue with. Its major draw telltale words and phrases that just scream, an AI wrote this. The paper calls out classic cliches like tapestry of color, or vague intensifiers like a profound sense of, or these very particular adverbs like unsettlingly that these models seem absolutely obsessed with. Okay, moving on. To even begin to fix the problem, they first had to measure it. And this involved a really deep, almost forensic analysis to create what they call a slop fingerprint for different AI models, comparing their output directly against huge databases of human writing. Now, this really reveals the sheer scale of the problem we're talking about. In their analysis of one particular model, the researchers found that the name Alara appeared over 85,000 times more frequently in its stories than in all of the human text they analyzed. It's just an absolutely staggering fixation. And this table really drives home that the problem goes way beyond a single quirky name. Just look at this data. The word unsettlingly is overrepresented by almost 4,000 times. The three-word phrase heart-hammered ribs appears almost 1,200 times more often than it should. So this isn't just a hunch, it's a quantifiable statistical tick. So how in the world do you fix this? The paper's first idea is a pretty clever tool called the Antislop sampler. Basically, it's designed to catch and stop slop as it's being written right at inference time. It's a really elegant idea, but as we're about to see, it comes at a very steep price. Here's the breakdown of how it works. As the model is generating text token by token, the sampler is watching. The second it detects a banned phrase, say voice barely, it immediately backtracks to the token that started it, which would be voice. It then penalizes the probability of that token and forces the model to resample, to pick a different, hopefully more original word to continue with. It's kind of like an automated undo and rewrite button. But, and this is a big but, here's the catch. This chart shows us the speed, or the token rate, of the different methods. The baseline model is way over on the left, running blazing fast. But as you add more and more banned words to the Antislop sampler, look what happens. The speed just plummets. With a big ban list of 8,000 patterns, the throughput drops by a catastrophic 96%. Yeah, it works, but it's just way too slow for most real-world applications. And that brings us to the core innovation of the paper. Since fixing the problem during generation was too slow, the researchers developed a way to permanently train these bad habits out of the model itself. It's a totally new fine-tuning method they call Final Token Preference Optimization, or FTPO for short. Now, the crucial thing to understand is how this is different from older methods like, say, Direct Preference Optimization, or DPO. The best way to think about it is this. DPO is a hammer. It makes these big, coarse adjustments to the whole model, which can cause all sorts of collateral damage and actually make it worse overall. FTPO, on the other hand, it's a scalpel. It performs precise, logit-level surgery to fix the problem without harming the model's other abilities. And here's the formal definition. FTPO operates directly on the model's logits, and those are just the raw probability scores for every possible next word. It basically teaches the model, hey, when you're about to say Ilara, I want you to strongly dislike that choice, and instead prefer these other better options. And it does this surgically, only adjusting the logits it absolutely needs to, which is the key to avoiding that collateral damage. Okay, time for the results. A scalpel is only useful if the surgery is actually a success, right? So the researchers put FTPO through a whole battery of tests against other methods to see if it really delivered on its promise. High slop suppression with low damage. And here's the proof in the pudding. This chart is the key. What it shows is that FTPO, that's the scalpel method, achieves over a 90% reduction in slop. But look at the other axis. It does this with virtually no loss in overall writing quality. Meanwhile, the other methods, like DPO or just straight-up token banning, they might suppress the slop, but they cause a huge drop in quality. FTPO is the only one that gets the best of both worlds. And what's really cool is that this technique isn't just for single words. Check this out. This chart shows how often different models use the not X, but Y sentence structure. Some models overuse it like crazy compared to the human baseline. With Antislop's system, they can target and completely eliminate this complex stylistic pattern, dropping its usage all the way down to 0. Now this chart, a dendrogram, might just be the most intuitive proof that FTPO works. Think of it like a family tree for writing styles. See how all the standard AI models are clustered together up top? That shows they all have similar non-human writing habits. But now look at the FTPO-tuned model, the one in red. It has been pulled out of that main AI cluster and now groups much, much more closely with the branch containing human authors like Mark Twain and Jane Austen. The surgery worked. It literally writes more like a human. So let's zoom out for our final section and really think about the bigger picture here. I mean, yes, this is a powerful way to fix a very specific, very annoying problem in AI writing, but the underlying technology, it's so much bigger than that. And this, right here, is the key takeaway. The real breakthrough isn't just about getting an AI to stop saying, shimmered. It's about developing a framework for fine-grained, surgical control over a model's output. It's a method for telling an AI not just what to do, but also with incredible precision, what not to do, without breaking everything else in the process. And that leaves us with one last, kind of provocative thought. This research has given us a scalpel for editing an AI's behavior. They started by cutting out stylistic cliches. But what's next? What other undesirable tendencies, from subtle biases to unhelpful conversational habits, could we surgically remove in the future? This paper really opens up a whole new world of possibilities.